Okay, so now we're going to talk about the geometric realization theorem. And it more or less says that if you give me an abstract simplicial complex, then I can construct a geometric realization of it in a sufficiently high-dimensional Euclidean space. Okay, so the statement is that every abstract simplicial complex of dimension d has a geometric realization in R2D plus 1. Okay, all right, so let's try to prove this. Okay, so let's consider a map from the vertex set of this abstract simplicial complex. Well, I should call that simplicial complex A. Right, so let's consider a map F from the vertex set of A to R2D plus 1. And what we want is that you want the image of this vertex set to be a set of points in R2D plus 1, which are in what are called general position. So whose image is in general position. And what it basically means is that if you recall, when you have a ambient space which is dimension 2D plus 1, then of course you know that you can have at most 2D plus 1 linearly independent vectors, or you can have 2D plus 2 affinely independent points. Okay, so what you want basically is that you want this image to be such that if you pick any 2D plus 2 points in that image, right, 2D plus 2 unique points in that image, then that set of points is affinely independent. Okay, so that's to say that any 2D plus 2 or fewer points in the image are affinely independent. Of course, they have to be distinct points, but okay, so that's what's meant by general position. Okay, so they don't have any sort of strange degeneracies. And you can usually, it's like perturb, it's like any candidate map, it's like so that you have something which is in general position. Okay, so anyway, so let's say that you have two abstract simplices in the simplicial complex, and the abstract simplicial complex, let's call them alpha and alpha 0, B and A. Okay, then you know the following, that the cardinality of the union, right, is of course equal to nothing more than the cardinality of one of the sets plus the cardinality of the other set minus the cardinality of the intersection. Okay, and because, okay, so this is of course at sort of greater than or equal to 0, all right, and then these cardinalities are bounded from above by d plus 1. Well, okay, they're less than or equal to d plus 1. So this cardinality is less than or equal to 2 times d plus 1. Okay. All right. So in any case, you have 2d plus 2 points, right? And by the assumption that this vertex map is going to have an image which is in general position, those points are going to be affinely independent, right? So the points in sort of f of alpha union alpha 0, right, are affinely independent. Okay, and so a consequence of this then is that every convex combination, it's like of points in this set, is unique. So there's a unique representation, if you will, right? Okay, all right. So, so we have to check basically the condition more or less that if you have, you know, the image of these two things, right, that the intersections are, you know, a face, it's like of both of these, or the empty set, right? So, okay. So let's say we have a point in two of the simplices, sigma, which is the convex hull of f alpha, and it is also in sigma 0, which is again the convex hull of f applied to alpha 0 now. Okay. Okay. So so if you have these two things, okay, then you know that clearly it has to be in the convex hull of the union, right? So so we know that x is an element of convex hull of f alpha union alpha 0, right? But then since f union f of alpha union alpha 0, it's like is a set of affinitely independent points, you have this unique representation as this convex combination. So x is equal to sort of lambda I ui, where ui is in the union alpha union alpha 0. Okay, and there's a unique representation, right? So in particular, since you can write alpha as things in each of these convex hulls, right, it has to be that you can actually write x in the intersection and not just the union. Okay. So since x is an element of the intersection, right, it implies that x actually can be written as a sum over ui, where alpha ui is in the intersection and not just in the union. Okay, and of course this, right, is an element of the convex hull of f alpha intersection alpha 0, right? Okay, so what this means then is that okay, so what this means is that the intersection of sigma with sigma 0 is either empty or the common face convex hull of f, again alpha intersect alpha 0. Okay, so so that tells you then that you then have an honest to goodness geometric realization of the abstract simplicial complex A in an embedding space which is R to the 2D plus 1. Okay, so that's basically a proof of the geometric realization theorem, and that every abstract simplicial complex of finite dimension has a geometric realization. So let me just stop here.